Imagine a planet almost exactly the same size as Earth, same rocky composition, born from the same cloud of dust and gas, in the same solar system, practically next door. Scientists believe it once had liquid water, it may have had oceans for 2 billion years, and then something went catastrophically wrong. Today, its surface is hot enough to melt lead. Its atmosphere would crush you with the weight of almost a kilometer of ocean above your head. Clouds of sulfuric acid circle the planet at hurricane speeds. The Soviet Union sent armored spacecraft to land on it. The strongest survived just over 2 hours before being destroyed. This is not a distant alien world. It is our nearest planetary neighbor. And what happened to it is worse than you think. If this kind of deep science is something you come back for, go ahead and hit that like button and subscribe. It genuinely helps the channel grow and lets us keep making these. Are you comfortable? Now, let's begin. Most people, if you ask them to name the scariest planet in the solar system, would not say Venus. They would say Jupiter, with its storms larger than Earth. They would say Saturn, with its radiation belts and violent wind systems. Some might say Neptune, impossibly cold and impossibly far. A few might say Mars, barren and lifeless and coated in toxic dust. Almost nobody picks Venus, and that is the first problem, because Venus is not just another planet with extreme weather or a harsh surface. Venus is what happens when an Earth-like world fails completely. And the fact that most people do not know this, the fact that Venus hides behind a name associated with beauty and a reputation as nothing more than a bright dot in the evening sky, is part of what makes it so disturbing. Let us start with what most people think they know. Venus is the second planet from the Sun. It is sometimes called the morning star or the evening star, because it is often the brightest object in the sky after the Sun and the Moon. It is hot, it has clouds, it is somewhere near Earth. If you paid attention in school, you might remember being told it is roughly the same size as Earth, and that it is sometimes nicknamed Earth's twin or Earth's sister. That is usually where the description stops. Hot planet, bright light, kind of like Earth, but not really. Move on. The textbook flips to Mars, because Mars is where the rovers are, where the photos come from, where the dreams of colonization live. That shallow sketch of Venus is not wrong. It is just so incomplete that it borders on dangerous, because what Venus actually is, what it actually represents in the context of planetary science, is one of the most unsettling objects humans have ever studied. And the reason it is unsettling has almost nothing to do with the fact that it is hot. Here is where the real story begins. Venus and Earth are not vaguely similar. They are structurally almost identical. Venus has a diameter of approximately 12,104 kilometers. Earth has a diameter of approximately 12,756 kilometers. The difference is roughly 5%. In planetary terms, that is nothing. If you could hold both planets in your hands, you would struggle to tell them apart by size alone. The mass of Venus is approximately 81.5% of Earth's mass. Its density, its bulk composition, the ratio of rock to metal in its interior, all of these overlap with Earth so closely that no other planet in the solar system comes remotely near matching them. Mars is too small. Mercury is too small and too dense in the wrong proportions. The gas giants are not even in the conversation. Venus is the only rocky world in our neighborhood that genuinely mirrors Earth in the measurements that matter most for determining what kind of planet something is. And the similarities do not stop at size and composition. Venus formed from the same region of the protoplanetary disk that produced Earth. The cloud of gas and dust that collapsed to form our Sun roughly 4.5 billion years ago left behind a spinning disk of material, and from that disk, the rocky planets condensed. Venus and Earth formed from essentially the same ingredients, in the same oven, at roughly the same time. They are not distant cousins, they are siblings. Born from the same material, shaped by the same physics, separated by only about 41 million kilometers at their closest approach. That is close. In a galaxy where distances are measured in light years, and the nearest star beyond our own is over 4 light years away, Venus is right next door. Light from the Sun takes about 6 minutes to reach Venus, and about 8 minutes to reach Earth. The difference in their orbital distance from the Sun is roughly 30%. Venus orbits at an average of about 108 million kilometers. Earth orbits at about 150 million kilometers. That gap matters enormously for reasons we will get to. But in structural terms, in terms of what these planets are made of and how big they are, Venus and Earth started from nearly the same blueprint. This is the detail that changes everything about how you should think about this planet. Venus is not some alien world born under exotic conditions in a distant part of the solar system. It is Earth's nearest equivalent. It is the planet that, by every reasonable expectation, based on its size, mass, composition, and origin, should have turned out the most like ours. And instead, it turned out to be one of the most hostile environments ever measured by human instruments. That gap between expectation and reality is where the horror lives. Think about what that means in concrete terms. If you lined up every planet and major moon in the solar system and asked a physicist to predict, based purely on mass, radius, density, and distance from the Sun, which world would most closely resemble Earth, the answer would be Venus, without hesitation. Mercury is too small, too close to the Sun, and has essentially no atmosphere. Mars has roughly 1/10 of Earth's mass and a thin atmosphere that offers almost no surface pressure. The gas and ice giants are not even comparable. Europa and Titan are moons, not planets, and their compositions are dominated by ice rather than rock and metal. Venus alone matches Earth in the fundamental physical parameters that determine what a rocky planet can become. Its surface gravity is approximately 8.87 meters per second squared, compared to Earth's 9.81. A person who weighs 180 pounds on Earth would weigh roughly 163 pounds on Venus. You would feel lighter, but not dramatically so. The experience of standing on Venus, in terms of how gravity pulls on your body, would feel almost normal. That detail makes the environment even more psychologically unsettling. The gravity feels like home. Everything else is trying to kill you. Now, there is another piece of this that most people have never encountered. For a long time, scientists assumed Venus had always been the furnace it is today. Closer to the Sun, too much heat, no chance for water, end of story. That assumption has been substantially revised. In 2016, researchers at NASA's Goddard Institute for Space Studies published climate modeling work suggesting that Venus may have had a shallow liquid water, ocean, and habitable surface temperatures for up to 2 billion years of its early history. 2 billion years. That is not a brief window. That is nearly half the current age of the planet. The models showed that Venus's slow rotation, the fact that it turns so sluggishly that a single rotation on its axis takes 243 Earth days, would have produced thick dayside cloud cover that reflected enough sunlight to keep surface temperatures moderate. Under those conditions, Venus could have had a climate not dramatically different from Earth's. This means the planet you see glowing in the evening sky may have once had coastlines. It may have had rain. It may have had weather systems that a human being, transported back in time billions of years, would have found recognizable. It may have had shallow seas where sunlight reached the bottom, where the chemistry of life as we understand it could theoretically have taken root. The research is modeling-based, not confirmed by direct observation, and the question of whether Venus truly had a prolonged habitable period is still actively debated among planetary scientists. Other models suggest Venus may have lost its water much earlier, before it ever had a chance to form stable surface oceans. The debate is not settled. But the possibility alone, the mere scientific plausibility that Venus was once temperate, reshapes the entire meaning of the planet, because it means Venus did not start out as a nightmare. It may have started out as something remarkably close to home, and then it transformed into what it is now. That transformation is the real story. And it is far worse than a simple rise in temperature. But before we reconstruct how it happened, you need to understand what Venus actually is today. Not the postcard version, not the line in a textbook. The real thing, as measured by the only machines that have ever touched its surface. Between 1961 and 1984, the Soviet Union launched a series of spacecraft toward Venus under the Venera program. It was one of the most ambitious and least remembered achievements in the history of space exploration. More than a dozen missions were directed at Venus across more than 2 decades of effort. The early missions failed spectacularly. Venera 1 through 6 either lost contact during cruise, were crushed during descent through the atmosphere, or transmitted only briefly before being destroyed by conditions that the engineers had not fully anticipated. Each failure returned data. Each failure taught the design teams something new about what they were up against. And what they learned, mission after mission, was that Venus was worse than they had imagined. Every single time. The engineering teams kept iterating. They built stronger titanium pressure vessels. They added more thermal insulation. They redesigned the cooling systems to pre-chill the interior of the lander before atmospheric entry, buying precious extra minutes of operational time on the surface. They treated Venus not as a destination, but as an adversary, something that had to be endured and outlasted rather than simply reached. The landers were not designed to operate indefinitely. They were designed to survive long enough to take a few measurements and transmit them home before the planet inevitably won. Venera 7, in 1970, became the first human-made object to transmit data from the surface of another planet. It survived for approximately 23 minutes on the ground. The data it returned confirmed surface temperatures of approximately 475 degrees Celsius and a surface pressure of roughly 90 times Earth's atmospheric pressure. Those numbers, when they arrived at mission control, were difficult for some engineers to believe. 90 atmospheres of pressure is not a number that has any analog in human surface experience. It is the pressure you would feel roughly 900 meters beneath the surface of Earth's ocean. No human has ever free-dived to that depth. No unprotected submarine hull built for crewed operations regularly operates at that depth. The deepest point in Earth's ocean, the Challenger Deep, reaches a pressure of roughly 1,100 atmospheres, but that is nearly 11 kilometers down. Venus achieves the crushing force of a deep ocean environment at its surface, under open sky, everywhere on the planet, at all times. Venera 9, in 1975. Returned the first photograph ever taken from the surface of another planet. The image showed a landscape of flat, angular rocks stretching to the horizon under a dim, orange-brown sky. The rocks appeared sharp-edged, relatively unweathered in the way that Earth rocks are rounded by water and wind over time, suggesting a surface shaped by volcanic processes and chemical erosion, rather than the familiar hydrological cycle that sculpts landscapes on our world. The light levels on the surface of Venus are comparable to an overcast day on Earth, despite the planet being closer to the Sun, because the atmosphere is so thick and the cloud cover so total that less than 3% of incoming sunlight reaches the ground. The sky is not black like the moon's. It is not blue like Earth's. It is a deep, oppressive amber, permanently glowing with the diffused remnants of sunlight that has been scattered and filtered through more than 60 kilometers of cloud and haze. You would not need a flashlight to see. But you would not see a blue sky, a sun, a star, or a horizon line beyond the dense haze. You would see rock, dim orange light, and an oppressive closeness that has no equivalent on any world humans have ever set foot on. The photographs from Venera 9 and the missions that followed remain, to this day, the only direct images of Venus's surface ever taken. No mission since 1985 has attempted to land there. Venera 13, launched in 1981 and arriving at Venus in 1982, was the most successful surface lander in the program. It transmitted color photographs and sound recordings from the surface for approximately 127 minutes, 2 hours and 7 minutes. That was the longest any human-made object has ever survived in direct contact with the surface of Venus. The spacecraft was built like an armored diving bell, encased in a pressure hull designed to withstand forces that would implode a conventional submarine. It carried a pre-cooling system that chilled its interior before entry, creating a thermal buffer that would be slowly consumed as the heat of Venus seeped inward through the hull. It was designed from the start to be destroyed. Every instrument was on a countdown from the moment it touched the ground. Every measurement was borrowed time. The engineers knew with certainty that the planet would win. The only question was how much data they could extract before it did. And even with every engineering precaution the Soviet space program could devise, even with decades of accumulated knowledge from prior failures, the planet killed it in just over 2 hours. Here is the detail from Venera 13 that rarely gets mentioned but changes how you understand the environment. The lander recorded sound during its descent and on the surface. The audio captured what researchers described as a low, steady hiss, consistent with the dense atmosphere flowing over the spacecraft's hull. At 90 atmospheres of pressure, the carbon dioxide atmosphere is so thick that it behaves less like air and more like a fluid. The density of the near-surface atmosphere on Venus is roughly 6.5% that of liquid water. You would not walk through it the way you walk through air on Earth. You would push through it. Every movement would meet resistance. The wind speeds near the surface are low, only about 1 to 2 meters per second, which sounds gentle until you account for the density. A breeze of 1 meter per second in an atmosphere that dense carries the force of a much stronger wind on Earth. Researchers studying regional wind patterns on Venus's surface have found that even at such low velocities, the dense atmosphere generates enough energy to transport sand-sized particles across the highland plateaus, creating localized dust movement events. The planet is not still. Even at the bottom of that crushing, superheated column of gas, the environment moves, erodes, and reshapes the surface. Now, consider what those conditions mean in combination. 475 degrees Celsius is well above the melting point of lead, which melts at approximately 327 degrees Celsius. It is above the melting point of zinc. It is above the melting point of tin. It is approaching the range where some aluminum alloys begin to lose structural integrity. This is not simply hot. This is metallurgically destructive. A block of lead placed on the surface of Venus would soften and deform. Many standard electronic components would fail instantly. Solder, the material used to join circuits in nearly every electronic device on Earth, would be liquid. The operating environment is not just hostile to biology. It is hostile to machines, to metals, to materials science itself, and the temperature is not the only chemical threat at the surface. The atmosphere is approximately 96.5% carbon dioxide, with most of the remainder being nitrogen. But traces of sulfur dioxide, hydrogen sulfide, and other sulfur compounds permeate the lower atmosphere, contributing to a cocktail of reactive chemistry that has no equivalent on any other known planetary surface. Near the surface, the carbon dioxide atmosphere is so dense and so hot that it has crossed into a physical state where the gas itself becomes chemically aggressive. It is not simply pressing on everything from above. It is interacting with everything it touches, penetrating surfaces and dissolving compounds through reactions that do not occur in any normal atmospheric environment. Materials that would be perfectly stable in ordinary air, even extremely hot air, undergo corrosion and degradation on Venus because the atmosphere at those pressures and temperatures is no longer behaving like a gas in any familiar sense. It is behaving like a solvent. The details of that transition, what the atmosphere actually becomes in the final kilometers above the surface, are part of what makes the descent through Venus so much worse than a simple temperature reading suggests. But the implication at the surface is immediate. The atmosphere of Venus does not merely surround you, it attacks you. It is an environment that actively degrades the structural integrity of nearly anything placed within it. This is the first critical realization that separates the real Venus from the cartoon version. The danger is not one thing. It is not the temperature alone. It is not the pressure alone. It is not the chemical composition alone. It is all of them operating simultaneously, reinforcing each other, creating an environment where each individual extreme makes the others worse. The heat makes the chemical reactions faster and more aggressive. The pressure makes the atmosphere denser, which makes it more effective at transferring heat, which makes the surface temperature more uniform, which means there is no refuge anywhere on the planet, dayside or nightside, pole or equator. The chemistry makes the atmosphere more opaque, which traps more heat, which maintains the pressure. Every element of the system feeds every other element. It is not a collection of hazards, it is an integrated machine of destruction, and Venus does not even give you the mercy of variation. On Earth, if one region is too hot, you move to a cooler one. If the equator is baking, the poles offer relief. If the day side is scorching, you wait for night. Venus offers none of this. The surface temperature is approximately 475 degrees Celsius everywhere, at the equator, at the poles, on the day side, on the night side. The atmosphere is so massive, so thermally sluggish, that it acts as a planetary heat reservoir of almost incomprehensible efficiency. The planet rotates so slowly, taking 243 Earth days to complete a single rotation, that you might expect the night side to cool substantially during its months-long stretch of darkness. It does not. The atmosphere circulates heat so effectively that the temperature difference between the hottest and coldest points on Venus's surface is negligible. There is no cool spot. There is no shadow deep enough. There is no cave, no valley, no polar region that offers even a few degrees of relief. The entire surface of the planet is locked at the same killing temperature permanently, with no mechanism for change. This is what people miss when they hear Venus is the hottest planet in the solar system. They picture a desert. They picture Death Valley turned up to 11. That image is completely wrong. A desert has cool nights. A desert has shade. A desert has wind patterns that shift temperature across regions and seasons. Venus has none of that. It is thermally flat. It is a world where the concept of weather, in the sense of changing conditions that offer alternating relief and challenge, does not exist at the surface. What exists instead is a single, permanent, planet-wide state of extreme hostility that does not fluctuate, does not cycle, does not offer any window of survivability, no matter where you are or when you arrive. consider the contrast with every other world we know. Mercury, the closest planet to the Sun, has surface temperatures that swing from approximately 430 degrees Celsius on its sun-facing side to negative 180 degrees Celsius on its dark side. Mercury is scorching and freezing, depending on where you stand. Mars has temperature ranges from roughly 20 degrees Celsius at the equator on a summer afternoon to negative 120 degrees Celsius at the poles in winter. Earth, obviously, has tropical heat and polar ice and everything between. Every rocky body in the solar system, without exception, offers at least some thermal variation across its surface. Every one except Venus. Venus has taken the energy it receives from the Sun and, through the sheer mass and opacity of its atmosphere, distributed it so uniformly that the planet has been turned into a single temperature object. It does not have hot spots and cold spots. It has one spot, and that spot is 475 degrees Celsius. Everywhere, always. And here is something that sharpens the picture even further. Venus does not have an intrinsic magnetic field, Earth does. Earth's magnetic field is generated by the churning of liquid iron in its outer core, and it forms a protective bubble around the planet that deflects the charged particles streaming outward from the Sun in the solar wind. That magnetic shield is one of the reasons Earth still has a thick atmosphere and surface water. It prevents the solar wind from stripping away atmospheric gases over time. Venus has no such protection. Its interior has cooled to the point where it cannot generate a self-sustaining magnetic dynamo. Instead, it has only a weak, induced magnetosphere created by the interaction between the solar wind and the planet's upper atmosphere. That interaction ionizes atmospheric gases, producing a thin, unstable magnetic drape that provides vastly less protection than Earth's field. The consequences of this are measurable and ongoing. Without that magnetic shield, the solar wind interacts directly with Venus's upper atmosphere, and spacecraft observations have confirmed that the planet is actively losing atmospheric material to space right now. Not just lightweight hydrogen, which escapes easily from any unprotected atmosphere, but heavier atoms that should be far more difficult to strip away. The mechanisms driving this loss are still not fully understood, which makes the process more concerning, not less. Something is pulling material out of Venus's atmosphere with more force than current models fully explain. The process that helped destroy Venus's habitability billions of years ago has not stopped. It is still operating, still eroding what remains, and Venus has no defense against it. And it is not just the surface that tells this story. The erosion from above, the hostility below, and the locked chemistry in between form a single integrated system. This is the picture that begins to take shape when you move past the textbook summary. Venus is not merely a hot planet. It is a planet where the surface would crush you, cook you, and chemically dissolve your remains simultaneously. Where the atmosphere is so dense it behaves like a fluid. Where the clouds are made of sulfuric acid. Where the temperature does not vary from place to place or from day to night. Where no magnetic field protects what remains of the atmosphere from being slowly peeled away by the star next door. Where every spacecraft humanity has ever landed has been destroyed within hours. And where the conditions are not a collection of independent problems, but an interlocking system where each extreme sustains and worsens every other. Most descriptions stop here. They give you the headline numbers, the comparison to hell, the note about melting lead, and they move on. But stopping here means missing what makes Venus truly frightening. Because everything described so far is what Venus is. The deeper question, the one that actually keeps planetary scientists awake, is how it got this way. How a world that may have once had liquid water and moderate temperatures, and a climate not so different from Earth's, crossed a threshold and became this. The surface conditions alone are staggering. But the atmosphere above the surface is its own layered architecture of danger, where each altitude introduces a new threat, where the chemistry shifts and intensifies in ways that no single description of temperature or pressure can capture. What exactly is waiting between the cloud tops and the ground, and how each layer of the atmosphere compounds the danger into something that the word hostile does not begin to cover, is something most descriptions of Venus never fully explain. That is where we go next. There is a place on Venus where the air temperature sits between roughly 30 and 70 degrees Celsius. The atmospheric pressure is close to what you feel standing at sea level on Earth. The sky is hazy but bright. If you were somehow floating at this altitude, roughly 50 to 55 kilometers above the surface, and you ignored the chemistry of what you were breathing, you might briefly mistake the conditions for an unpleasant but survivable day on your home planet. The temperature would remind you of a desert. The pressure would feel normal against your body. Gravity, at roughly 90% of Earth's, would feel almost identical to what you experience every day. This is not a coincidence or a curiosity. It is the reason that a handful of scientists have seriously proposed that the cloud layer of Venus might be the most accessible off-world environment for human exploration in the entire solar system, more reachable in some respects than the surface of Mars. A habitat floating at this altitude, suspended by buoyancy in the dense Venusian atmosphere, would face engineering challenges far less extreme than anything on the surface below. The concept has been explored in NASA studies. It is not science fiction. It is real engineering analysis applied to a real atmospheric layer. But that layer is a thin band of deception wrapped around a planet that is trying to kill everything inside it. And the moment you begin descending from that altitude, the deception ends. What replaces it, kilometer by kilometer, is a sequence of escalating conditions so hostile and so layered that no single description captures the full picture. The only way to understand it is to go through it. From the top of the atmosphere down to the rock, the descent begins in the upper cloud deck, which extends from roughly 65 kilometers above the surface down to about 48 kilometers. This is the layer that gives Venus its brilliant white appearance when viewed from space. Venus is one of the brightest objects in Earth's night sky, precisely because of these clouds. They reflect roughly 75% of all incoming sunlight back into space, making Venus more reflective than any other planet in the solar system. From a distance, this brilliance is beautiful. Up close, the composition tells a different story. The clouds of Venus are not made of water. They are composed primarily of concentrated sulfuric acid droplets, mixed with smaller amounts of other sulfur compounds. Sulfuric acid is one of the most corrosive substances commonly encountered in industrial chemistry on Earth. It is used to strip metal, dissolve organic material, and clean surfaces by chemically destroying contaminants. On Venus, this substance forms the dominant cloud layer that wraps the entire planet in a permanent, unbroken shroud. There is no gap in the coverage. There is no clear sky on Venus, anywhere, ever. The planet has not seen direct, unfiltered sunlight on its surface for what may be billions of years. Within this cloud layer, something extraordinary is happening that scientists still do not fully understand. The upper atmosphere of Venus is rotating far faster than the planet itself. Venus turns on its axis once every 243 Earth days. That makes it the slowest rotating planet in the solar system. A single Venusian day, measured from sunrise to sunrise, lasts roughly 117 Earth days. But the cloud tops do not respect this glacial rotation. They whip around the entire planet in roughly 4 Earth days, driven by winds reaching speeds of up to approximately 360 kilometers per hour. This phenomenon is called atmospheric superrotation. and it is one of the great unsolved problems in planetary science. On Earth, the fastest atmospheric winds are found in narrow jet streams and in the cores of the most powerful hurricanes. The global atmosphere does not uniformly outpace the planet's rotation by a factor of 60. On Venus, it does. The entire upper atmosphere is a single high-speed conveyor belt circling the planet at velocities that have no equivalent in our experience. Research published in recent years using data from Japan's Akatsuki orbiter, which has been studying Venus since 2015, has mapped these wind patterns in detail and confirmed that the superrotation is a persistent, global-scale phenomenon, not a regional weather pattern. The mechanism driving it likely involves a complex transfer of momentum from solar heating and atmospheric tidal forces, but the complete explanation remains an active area of research. The sulfuric acid clouds are not passive. Within them, photochemical reactions driven by ultraviolet light from the sun produce a constantly shifting mix of sulfur compounds. There are dark streaks in the ultraviolet images of Venus that absorb radiation in patterns scientists have not been able to fully explain. Some researchers have proposed that these absorbers could be microbial life, organisms floating in the relatively temperate cloud layer and feeding on chemical energy. That hypothesis remains deeply speculative and is not supported by confirmed evidence, but the fact that it is discussed at all tells you something about how strange the cloud chemistry of Venus truly is. The atmosphere is doing things we do not fully understand, at altitudes where conditions are, paradoxically, more Earth-like than anywhere else on the planet. Below the cloud base, at roughly 48 kilometers altitude, the haze clears and you enter the deep atmosphere. And this is where Venus stops resembling anything in human experience. The temperature at the cloud base is already roughly 170 degrees Celsius. The pressure is already several times that of Earth's surface, but you are still almost 50 kilometers above the ground. There is nothing below you but thickening, heating, compressing atmosphere stretching all the way to the rock. No more clouds, no more haze, just gas, growing denser with every kilometer of descent. As you fall through the next 20 kilometers, the temperature rises relentlessly. By 30 kilometers above the surface, it has passed 300 degrees Celsius. The pressure has climbed to roughly 10 to 15 times the pressure at Earth's sea level. The atmosphere around you is no longer something you would recognize as air. It is heavy. It resists movement. If you could somehow extend your hand into it at this altitude, you would feel it pushing back, not like wind, but like trying to push through a thickening fluid. The density of the atmosphere is increasing toward values that blur the boundary between gas and liquid. At approximately 20 kilometers above the surface, a threshold is crossed that has no analog on Earth and almost no analog anywhere else in the solar system. This is the altitude where the atmospheric pressure finally exceeds roughly 73 atmospheres. The temperature crossed the other required threshold, roughly 31 degrees Celsius, far higher in the atmosphere. But it is here, where both conditions are decisively met, that the carbon dioxide, making up 96.5% of the atmosphere, is fully in a supercritical state. Supercritical carbon dioxide is not a gas, it is not a liquid. It is a phase of matter that exists only above a specific combination of temperature and pressure, and it has properties of both states simultaneously. It fills a space like a gas, expanding to occupy every available volume. But it has the density and solvent properties of a liquid. It can dissolve substances. It can penetrate materials. It can corrode. On Earth, supercritical carbon dioxide is used in industrial processes precisely because of its unusual solvent capabilities. It is employed to decaffeinate coffee, to extract essential oils, and to clean precision components, all applications that exploit its ability to dissolve and transport materials that ordinary gas cannot touch. On Venus, This industrial solvent is the atmosphere. From roughly 20 kilometers altitude all the way down to the surface, everything on Venus exists immersed in a planet-wide bath of supercritical fluid that is simultaneously crushingly pressurized, blisteringly hot, and chemically reactive. This is a detail that almost never appears in popular descriptions of Venus. People hear that Venus has a thick carbon dioxide atmosphere. They picture something like a very smoggy day, or perhaps a room filled with dry ice vapor. That image is not even remotely close to reality. The lower atmosphere of Venus is a dense, corrosive, supercritical medium that would attack materials at the molecular level while simultaneously crushing and heating them. There is nothing on Earth that approximates this environment. The closest analogy would be the inside of a high-temperature industrial pressure reactor. Except the reactor is the size of a planet, and it never shuts off. The last few kilometers of descent bring the temperature to its final value. At the surface, it stabilizes at approximately 475 degrees Celsius. This number does not change. You already know why. The atmosphere's sheer mass and thermal inertia lock the surface into a single temperature everywhere on the planet, and nothing about the descent alters that conclusion. But experiencing it from above, having watched the temperature climb steadily for 50 kilometers of falling and arriving at a value that will not budge no matter how far you travel across the surface, makes the uniformity feel different than it does as a statistic. It is not just a number, it is a wall. There is no direction you can move, no time you can wait, no depth you can reach that offers anything other than 475 degrees Celsius. This thermal uniformity has a consequence that is easy to overlook. On Earth, the difference between hot and cold regions drives weather. Temperature gradients create pressure gradients, which create wind. This is why Earth has trade winds, monsoons, and storm systems. On the surface of Venus, there is almost no temperature gradient. At the surface, the wind barely moves. But you already know from what the Venera landers measured that even a sluggish breeze in an atmosphere this dense carries real physical force. What changes during the descent is the context. Up in the clouds, the wind screamed at hundreds of kilometers per hour. Down here, it has slowed to almost nothing. But the medium it moves through has become so heavy that the stillness is deceptive. The air does not need to move fast to push hard. The light reaching the surface is another element of the environment that defies expectation. The light at the surface has dimmed to something barely recognizable. What little sunlight survives, the journey down through the entire atmospheric column arrives as a deep orange glow, heavy and diffused, stripped of its original character by 50 kilometers of filtering. The visual environment is not dark, but it is alien in a way that photographs from the Venera landers only partially convey. There are no shadows with hard edges. There is no contrast between sky and ground. There is only the dim, even, amber saturation of a world permanently sealed beneath its own atmosphere. Now add one more layer to this picture. Venus has no intrinsic magnetic field. Earth generates a powerful magnetic field through the dynamo effect of its spinning liquid iron outer core. This field extends far into space and deflects the solar wind, the continuous stream of charged particles pouring outward from the sun. Without this magnetic shield, the solar wind would interact directly with Earth's upper atmosphere, stripping away lighter gases and gradually eroding the atmosphere over geological time. This is believed to be a significant factor in what happened to Mars, which lost its global magnetic field billions of years ago, and subsequently lost most of its atmosphere, leaving behind the thin, cold remnant it has today. Venus does not have this shield. Its core, though believed to be similar in composition to Earth's, does not generate a global magnetic field. The most likely explanation is that Venus's interior has cooled differently from Earth's, possibly because the lack of plate tectonics reduces the rate of heat loss from the mantle, creating conditions in the core that do not sustain the convective dynamo that Earth's core maintains. Without plate tectonics stirring the mantle and drawing heat outward, Venus's deep interior may have settled into a thermal state that simply cannot produce the necessary fluid motion. The result is that the solar wind hits Venus's upper atmosphere directly. And in 2024, the European Space Agency and JAXA's Bepi-Colombo mission, during a flyby on its way to Mercury, made a striking discovery in a previously unexplored region of Venus's magnetic environment. The spacecraft detected positively charged carbon and oxygen ions being accelerated to speeds fast enough to escape the planet's gravitational pull entirely. This was the first time carbon ions had ever been observed escaping from Venus. The solar wind was actively stripping atoms from the top of the atmosphere and flinging them into space. This finding, published in Nature Astronomy, confirmed what planetary scientists had long suspected but had not observed with this level of detail. Venus is still losing its atmosphere to space. Not quickly enough to strip the planet bare in any human time frame, the atmosphere is far too massive for that, but continuously, persistently, in a process that has been ongoing for billions of years. In the deep past, this atmospheric escape played a crucial role in the loss of Venus's water. Ultraviolet radiation from the sun split water molecules into hydrogen and oxygen. The lightweight hydrogen atoms rose to the upper atmosphere, and without a magnetic field to hold them in, they were carried away by the solar wind. Over geological time, Venus lost virtually all of its water this way. The hydrogen floated up and was blown off. The oxygen either escaped as well or was absorbed into surface rocks through chemical reactions. The evidence for this ancient water loss is written in the atmosphere itself. Venus has an extraordinarily high ratio of deuterium to ordinary hydrogen, roughly 150 times the ratio found on Earth. Deuterium is a heavier isotope of hydrogen. Because it is heavier, it is harder for the solar wind to carry away. Over billions of years, as ordinary hydrogen was preferentially stripped from the atmosphere, the proportion of deuterium left behind increased. That elevated ratio is a chemical fingerprint of massive water loss. It tells scientists that Venus once had far more hydrogen, and therefore far more water, than it has today. The water is gone. The signature of its departure remains. What this means in practical terms is that Venus is not merely a hot planet with a thick atmosphere. It is a planet that has been under sustained assault from its own star for billions of years, with no magnetic field to deflect the attack, and which has already lost one of the most critical substances for habitability as a direct result. The sun stripped Venus of its water, and Venus had no defense. That loss then cascaded into every other system on the planet, as we will explore in detail. But the point to register now is that the hostility of Venus is not limited to conditions at the surface. It extends upward into space, where the interaction between the solar wind and the unprotected atmosphere continues to erode the planet even today. Let us now assemble the full picture of what a descent through Venus actually means, because the individual facts only become truly disturbing when you see them stacked. You enter the atmosphere and encounter sulfuric acid clouds that wrap the planet completely, blocking direct sunlight and creating a permanent chemical haze. These clouds are driven by winds moving at hundreds of kilometers per hour in a super-rotating system that outpaces the planet's own rotation by a factor of 60. Below the clouds, you enter clear atmosphere, but the temperature is already hot enough to bake ceramics. The pressure is already several times Earth's sea level. With every kilometer of descent, both values increase. By the time you are 20 kilometers above the surface, the atmosphere around you has become a supercritical fluid, a dense, chemically reactive medium with the dissolving power of an industrial solvent. The temperature has passed 400 degrees Celsius. The pressure is approaching 80 times Earth normal. The light has dimmed to an orange twilight. You are still 20 kilometers from the ground. At the surface, the temperature is 475 degrees Celsius. The pressure is approximately 90 atmospheres. The atmosphere is a supercritical carbon dioxide medium with trace reactive compounds. The wind is slow, but carries the force of a heavier breeze because of the atmospheric density. The light is dim, orange, filtered through the entire atmospheric column above. The ground beneath you is basaltic rock, chemically weathered by the corrosive atmosphere, in a landscape of volcanic plains and deformed mountains that have never felt rain, never seen open sky, never experienced a temperature below several hundred degrees in potentially hundreds of millions of years. Above you, the sulfuric acid clouds churn. The solar wind blasts the upper atmosphere. Carbon and oxygen ions are being stripped away and flung into the void. The planet rotates so slowly that a single day-night cycle takes longer than a Venusian year, and the entire system is thermally locked. The heat cannot escape. The atmosphere traps it, redistributes it, holds it against the surface like a suffocating blanket with the weight of an ocean. No spacecraft built by any nation on Earth has survived this environment for longer than roughly 2 hours. The most advanced Soviet landers, specifically designed for these conditions, transmitted data for barely more than 120 minutes before the heat penetrated their insulation and destroyed their electronics. These were not delicate instruments. They were titanium-armored pressure vessels pre-cooled to low temperatures before entry, engineered to a specification that would survive conditions more extreme than any environment encountered in earthly industry. Venus killed them anyway. In about the time it takes to watch a long film, the planet reduced the most rugged machines humanity had ever built to inert metal sitting on hot rock, and that is with passive endurance. If you wanted to do active science on the surface, to rove, to drill, to conduct long-term monitoring, the engineering challenges multiply beyond current capability. Every electronic component must function at temperatures that would destroy standard semiconductors. Every mechanical joint must operate under pressures that would immobilize conventional designs. Every material must resist chemical attack from the supercritical carbon dioxide atmosphere and whatever trace reactive species it contains. The power system must generate energy in an environment where solar panels cannot see the sun and where the thermal gradient between inside and outside the spacecraft is extreme enough to stress any insulation system. This is why no nation has returned to the surface since 1985. It is not for lack of interest. It is because Venus defeats the engineering. The planet does not offer a foothold. It does not provide a crack in its defenses that clever design can exploit. It presents a comprehensive, overlapping, mutually reinforcing set of conditions that attack every system simultaneously. Heat destroys electronics, pressure crushes structures, the atmosphere corrodes materials, the acid clouds degrade anything that passes through them. The lack of a magnetic field leaves the upper atmosphere exposed to solar wind erosion, and the whole system is self-sustaining. The thick atmosphere maintains the heat maintains the atmospheric chemistry. The chemistry maintains the conditions that prevent the system from changing. This is what scientists mean when they call Venus a planetary failure state. It is not merely that one thing went wrong, it is that everything went wrong, and then each failure reinforced the others, creating a stable configuration of total hostility. The system locked. And once it locked, there was no mechanism available to unlock it. But describing the current state of Venus, as comprehensive and horrifying as it is, does not answer the question that sits at the center of this entire story. How did this happen? Venus and Earth started with nearly identical specifications. Same raw materials, same region of the solar nebula. Nearly the same size, the same density, the same bulk composition. And yet, the evidence suggests this planet was not always like this. As the evidence suggests, Venus may have once had liquid water, moderate temperatures, a functioning climate. The same research that revealed how long those conditions may have persisted also sharpened the central question that makes Venus so much more than an extreme weather curiosity. This is not a planet that was born hostile. It is a planet that became hostile. Something changed. Something tipped. And once it tipped, there was no going back. The story of how that happened, of how a world that may have looked remarkably like Earth transformed into the most hostile rocky surface in the solar system, is not a story about a single catastrophe. It is not quick, it is not simple, and it is not safely contained in the past. It is not an asteroid impact or a sudden explosion. It is a story about feedback loops, about systems that amplify their own changes, about a planet that gradually lost control of its own climate and then accelerated into a state from which there was no recovery. The sequence of events that turned Venus from a potential second Earth into the planet we have just descended through is one of the most important stories in all of planetary science, and recent discoveries, some published only in the last 2 years, have changed our understanding of how and when that transformation took place. But none of this explains the question that haunts planetary science. How did a world so much like Earth become this? 4.5 billion years ago, 2 planets formed side by side. They condensed from the same rotating disk of gas and dust surrounding a young star. They gathered their mass from the same reservoir of elements. Iron settled into their cores. Silicate minerals built their mantles. Rocky crusts solidified on their surfaces. When the process was finished, 2 worlds existed in neighboring orbits that were, by every meaningful structural metric, almost identical. Same class, same composition, same general blueprint. One of them became Earth. The other became the single most hostile rocky surface in the known solar system. And the question of how that divergence happened is not merely an academic puzzle. It is one of the most consequential questions in planetary science, because the answer determines whether Venus was doomed from the beginning or whether it fell into its current state through a chain of events that could, under different circumstances, happen to any Earth-like world anywhere in the universe. For decades, the standard explanation was straightforward and, in hindsight, too simple. Venus is closer to the Sun. It receives roughly 90% more solar energy than Earth. That extra energy made it too hot for liquid water to persist, so Venus never developed oceans, never developed a water cycle, and its carbon dioxide accumulated in the atmosphere unchecked, producing the greenhouse furnace we observe today. In this version of the story, Venus was never really Earth-like. It was always on the wrong side of an invisible line, the inner edge of the habitable zone, and its fate was sealed from birth. That version is almost certainly wrong. Or, at the very least, it is dangerously incomplete, and the evidence against it has been accumulating for years. In 2016, researchers at NASA's Goddard Institute for Space Studies published a study that used the same type of climate model employed to simulate Earth's future climate to instead simulate Venus's ancient past. They wanted to know whether Venus could have supported liquid water on its surface early in its history, despite being closer to the Sun. The answer was striking. Their models showed that Venus could have maintained a shallow ocean and surface temperatures comparable to Earth's for up to 2 billion years. The mechanism that made this possible was Venus's own slow rotation. Venus rotates extraordinarily slowly. A single rotation takes 243 Earth days, longer than its orbital year of 225 Earth days. This means a solar day on Venus, the time from one sunrise to the next, lasts roughly 117 Earth days. The GISS model showed that this slow rotation would have created a distinctive atmospheric circulation pattern. The prolonged daytime exposure would heat the surface and generate strong convective updrafts, producing a thick layer of reflective clouds on the sunlit side. Those clouds would have acted as a planetary sunshade, reflecting enough incoming solar energy back to space to keep the surface cool despite Venus's proximity to the Sun. The model produced mean global temperatures that were actually a few degrees cooler than present-day Earth, 2 billion years. If those models are correct, Venus was a temperate world with liquid water for almost half of the solar system's entire existence. It was not a briefly habitable flicker. It was a sustained, stable, potentially life-supporting environment that endured longer than the entire history of complex multicellular life on Earth. Multicellular organisms have existed on our planet for roughly 600 million years. Venus may have had habitable conditions for more than 3 times that span, and then it ended. Not in an instant, not in a dramatic cataclysm, in a slow, accelerating, self-reinforcing collapse that consumed the oceans, transformed the atmosphere, resurfaced the planet, and locked it into a state of permanent thermal extremity. Understanding how that collapse unfolded requires following a chain of cause and effect that begins with the Sun itself. Stars are not static, they brighten over time. As a main sequence star, like the Sun, converts hydrogen to helium in its core, the core gradually contracts and heats, increasing the rate of fusion and raising the total energy output. The Sun today is roughly 30% brighter than it was when the solar system formed. That increase has been gradual, approximately 6 to 0.7% per 100 million years, but over billions of years the cumulative effect is substantial. A planet that was comfortably within the habitable zone 4 billion years ago might find itself at the edge of that zone 2 billion years later, and beyond it 1 billion years after that. Venus, already closer to the Sun than Earth, was more vulnerable to this slow brightening. As solar luminosity increased, the amount of energy reaching Venus's surface gradually rose. For a long time, the climate system compensated. The reflective clouds adjusted. The atmospheric circulation adapted. The shallow ocean absorbed and redistributed heat. The system held. But every stable system has a threshold, and at some point, the incoming energy exceeded what the climate feedbacks could manage. Surface temperatures began to rise, and when they rose far enough, a feedback loop activated that would prove to be irreversible. Water vapor is a greenhouse gas. It is, in fact, the most potent greenhouse gas in Earth's atmosphere by total warming effect, more significant even than carbon dioxide in terms of the raw amount of infrared radiation it absorbs and re-emits. On Earth, the water cycle keeps this under control. Water evaporates, forms clouds, precipitates as rain, and returns to the surface. The total amount of water vapor in the atmosphere at any given time is regulated by this cycle. Temperature goes up slightly, more water evaporates, but the cycle returns it. The system is self-correcting within limits. On Venus, as the surface warmed past a critical threshold, the self-correction broke. More water evaporated from the surface. That additional water vapor in the atmosphere trapped more infrared radiation, which raised the temperature further, which evaporated more water, which trapped more heat. This is a positive feedback loop. a system where the output feeds back into the input and amplifies it. Each step makes the next step larger. Each degree of warming produces more water vapor, which produces more warming, which produces more water vapor. Scientists call this the runaway greenhouse effect, and it is the central mechanism in Venus's transformation. The term was first formalized by Caltech scientist Andrew Ingersoll in a 1969 paper specifically about Venus. The mathematics describe a limit, now called the Komabayashi-Ingersoll limit, above which a planet's outgoing infrared radiation cannot increase further, no matter how hot the surface becomes, because the atmosphere has become so opaque to infrared light that heat simply cannot escape. Once this limit is reached, there is no equilibrium. The surface temperature rises without bound until some other physical process intervenes. On Venus, the runaway greenhouse proceeded through a devastating sequence. As surface temperatures climbed, the oceans evaporated. Not suddenly, but progressively, over what may have been tens of millions to hundreds of millions of years. The water that had covered the surface moved into the atmosphere, initially as vapor, then rising higher and higher as the atmospheric temperature profile shifted. Once the water vapor reached the upper atmosphere, it encountered ultraviolet radiation from the sun, which broke the water molecules apart. Hydrogen and oxygen separated. The lightweight hydrogen atoms, freed from their molecular bonds, rose to the top of the atmosphere and were lost to space. This is where a discovery, published in 2024 in the journal Nature, becomes critically important to the story. For decades, scientists had calculated the rate at which Venus should have lost its hydrogen to space, and the numbers did not quite work. Standard models of hydrogen escape through known photochemical pathways produced loss rates that were too slow to account for the near-total desiccation of the planet within the available time frame. Something was missing from the models. The water was clearly gone. The deuterium to hydrogen ratio proved that, but the known mechanisms could not strip it away fast enough. Researchers at the University of Colorado Boulder, led by Michael Chafin, identified the missing piece. The molecule is called HCO+, formed when carbon dioxide and water interact in Venus's upper atmosphere. HCO+ undergoes a process called dissociative recombination, in which it captures a free electron and breaks apart, releasing a hydrogen atom with enough kinetic energy to escape the planet's gravity entirely. This chemical pathway had not previously been included in Venus atmospheric models. When Chafin's team incorporated it, the water loss rate increased dramatically, enough to account for Venus losing an entire Earth ocean's worth of water over geological time. This is not a minor refinement. It is a fundamental correction to our understanding of how Venus became desiccated. The HCO+ mechanism means Venus lost its water more efficiently than anyone had previously calculated. It means the window between the onset of the runaway greenhouse and the complete loss of the oceans may have been shorter than older models suggested. The planet may have crossed from habitable to dry faster than scientists thought possible. And once the water was gone, the real catastrophe began. On Earth, carbon dioxide is regulated by a complex system involving the ocean, the atmosphere, and the solid rock of the crust. Carbon dioxide dissolves in seawater, forming carbonic acid, which reacts with silicate minerals on the ocean floor and in continental rocks. These reactions lock the carbon into carbonate minerals, effectively burying it in solid rock. Over millions of years, plate tectonics carries those carbonate-rich rocks deep into the mantle through subduction zones, where heat and pressure release the carbon dioxide, which eventually returns to the atmosphere through volcanic eruptions. This is the carbon-silicate cycle, and it is one of the most important self-regulating mechanisms on Earth. When atmospheric carbon dioxide rises, temperatures increase, rainfall increases, weathering of silicate rocks accelerates, more carbon dioxide is pulled from the atmosphere and locked into rock, and temperatures come back down. The cycle acts as a planetary thermostat. Venus lost this thermostat. Without liquid water on the surface, there is no rain. Without rain, there is no chemical weathering of silicate rocks. Without weathering, there is no mechanism to pull carbon dioxide out of the atmosphere and bury it in carbonate minerals. The carbon-silicate cycle requires water at every step. When Venus lost its oceans, it lost the only process that could regulate the amount of carbon dioxide in its atmosphere. And there was a great deal of carbon dioxide to regulate. Both Earth and Venus are believed to have started with similar inventories of carbon. On Earth, most of that carbon is locked in rocks. Limestone, for instance, is calcium carbonate, and the total mass of carbon stored in Earth's crust and mantle is enormous. If you could somehow liberate all of that carbon and put it in the atmosphere as carbon dioxide, Earth's atmosphere would be roughly as thick and as dense as Venus's atmosphere is today. The raw carbon inventory is comparable. The difference is entirely about where the carbon resides. On Earth, it is safely locked in stone. On Venus, it is all in the air. Once Venus lost its water and its ability to sequester carbon, the carbon dioxide that had always been cycling through the system began to accumulate in the atmosphere. Volcanic outgassing continued to add carbon dioxide, as it does on any geologically active planet, but there was no longer any sink to absorb it. The atmospheric concentration climbed. With every increment of additional carbon dioxide, the greenhouse effect strengthened. Temperatures rose further. And the rising temperature ensured that the oceans, already evaporating, could never recondense. The water vapor in the atmosphere was eventually lost to space through the mechanisms described above, leaving behind an atmosphere dominated by carbon dioxide with almost no water remaining. The result was the atmosphere Venus has today, roughly 96.5% carbon dioxide. Pressure at the surface of approximately 90 atmospheres, a greenhouse effect producing approximately 500 degrees Celsius of warming above what the surface temperature would be without an atmosphere. For comparison, Earth's greenhouse effect produces roughly 33 degrees Celsius of warming. Venus's greenhouse warming is roughly 15 times more powerful than Earth's, but the atmospheric transformation was not the only change. The loss of water had consequences that reached deep into the planet's interior and altered the very geology of Venus in ways that made the transformation permanent. On Earth, water plays a critical role in the behavior of the mantle and crust. Water lowers the melting point of rock. It lubricates the boundaries between tectonic plates, allowing them to slide past and beneath each other. Plate tectonics as we know it on Earth depends on water. The subduction zones where one plate dives beneath another are lubricated by water-saturated minerals. Without this lubrication, the plates would be stiffer, more resistant to movement, and the entire tectonic system would behave differently. When Venus lost its surface water, it also gradually lost whatever water had been cycling into its mantle through geological processes. The mantle dried out, the crust became stiffer, and plate tectonics, if Venus ever had Earth-style plate tectonics, ceased. A 2025 study, published in Nature Communications by an international research team, systematically classified 6 distinct tectonic regimes for terrestrial planets, including a newly identified regime they called the episodic squishy lid. Their models showed that Venus's surface features, particularly the large circular structures called coronae that can exceed 1,000 kilometers in diameter, are highly consistent with this squishy lid regime. In this mode, the planet does not have the continuous, steady recycling of Earth's plate tectonics. Instead, magmatic intrusions from the mantle periodically weaken the rigid lid of the crust, producing regional, intermittent tectonic activity dominated by mantle plumes rather than plate boundaries. This has a critical implication for the carbon cycle. Without continuous plate tectonics, there is no steady subduction to carry carbon-bearing rocks into the mantle and recycle them. The carbon that is in the atmosphere stays in the atmosphere. The geological thermostat that regulates Earth's climate over millions of years does not exist on Venus. The carbon dioxide simply accumulates, and the planet has no mechanism to draw it back down. And there is new evidence that Venus's own geology may have actively contributed to the catastrophe rather than merely failing to prevent it. In 2025, a research team led by Alison Trussell at Arizona State University published a study in Science Advances that re-examined one of the most distinctive features on Venus's surface: the enormous channel-like structures called canali that stretch for thousands of kilometers across the volcanic plains. The longest of these, Baltis Vallis, extends over 6,800 kilometers, making it the longest volcanic channel in the entire solar system. Scientists had long debated what carved these channels. Trussell's team proposed an answer that connects directly to the atmospheric transformation. Using a combination of planetary mapping and lava flow modeling, they concluded that the channels were most likely carved by carbonatite lava, a rare type of lava that is unusually fluid, low in viscosity, and rich in carbon dioxide. On Earth, carbonatite eruptions are extremely uncommon, currently observed only at a single volcano in Tanzania, called Ol Doinyo Lengai. But the conditions on Venus may have favored widespread carbonatite volcanism. The critical detail is this: when carbonatite lava cools and solidifies, it outgasses carbon dioxide. If the canali on Venus were carved by extensive carbonatite eruptions, then the volume of lava required to create channels thousands of kilometers long would have released enormous quantities of carbon dioxide directly into the atmosphere. The study suggests that this volcanic outgassing may have been sufficient to account for the transformation of Venus's atmosphere from a potentially temperate state to its current dense, carbon dioxide-dominated condition. This finding shifts the story in an important way. It suggests that Venus's transformation was not solely driven by external factors like increasing solar luminosity. The planet's own internal geology may have actively pushed it over the edge. Volcanic processes generated the very carbon dioxide that thickened the atmosphere and intensified the greenhouse effect. The planet poisoned its own sky from below while the sun heated it from above. Two forces converging on the same outcome. And the volcanism has not stopped. In 2023, researchers analyzing archival radar data from NASA's Magellan mission, which mapped Venus's surface in the early 1990s, made a landmark discovery. They found a volcanic vent associated with the volcano Mart Mons that had changed shape significantly between two radar observations taken 8 months apart in 1991. The vent had doubled in size and appeared to be filled with a lava lake. Computer modeling of the observations showed that only a volcanic eruption could account for the changes. This was the first direct evidence that Venus is volcanically active today. Then, in 2024, a separate research team led by Davide Sulcanese of D'Annunzio University in Italy found additional evidence. Comparing different cycles of Magellan radar data taken between 1990 and 1992, they identified new lava flows on the western flank of the volcano Sif Mons and in the region of Niobe Planitia. The flows were estimated to cover between 30 and 44 square kilometers each, with depths of 3 to 20 meters. The researchers concluded that volcanic activity on Venus may be comparable in scale to volcanism on Earth. Venus is not geologically dead, it is actively erupting. It is still pumping carbon dioxide and other volcanic gases into an atmosphere that is already the thickest and most greenhouse-enhanced in the solar system. And because there is no water cycle, no chemical weathering, no plate tectonic recycling to remove that carbon dioxide, every molecule that comes out of the ground stays in the air. This is the self-reinforcing trap. The thick atmosphere keeps the surface hot. The hot surface keeps water from ever condensing. The absence of water prevents the carbon cycle from operating. The inactive carbon cycle allows carbon dioxide to accumulate. The accumulating carbon dioxide thickens the atmosphere further. And the ongoing volcanism continues to add more. Every component of the system reinforces every other component. There is no weak link. There is no single point where an intervention could break the loop. The system is locked. Scientists sometimes describe this in terms borrowed from systems theory. Venus has reached a stable equilibrium, but it is a stable equilibrium at catastrophic values. Like a ball that has rolled off a table and come to rest on the floor, it is stable on the floor. It is not going back to the table. The energy required to reverse the process, to somehow cool the atmosphere, recondense water, restart the carbon cycle, and re-establish a temperate climate would require planetary scale intervention beyond anything imaginable with current or foreseeable technology. The transformation is, for all practical purposes, permanent. Not permanent on the timescale of the universe, perhaps, but permanent on any timescale relevant to planetary habitability. There is one additional detail that deepens the horror of this story, and that is easy to overlook in the focus on atmosphere and temperature. Venus's surface shows a peculiar pattern in its crater distribution. Impact craters on Venus are distributed essentially at random across the surface, with no region showing significantly more or fewer craters than any other. And the total number of craters is relatively low, suggesting that the visible surface is geologically young, estimated at somewhere between 300 million and 700 million years old. This has led to a hypothesis that is still debated but widely discussed. At some point in Venus's relatively recent geological past, possibly within the last 500 million to 700 million years, the planet underwent a catastrophic resurfacing event. Massive volcanic eruptions may have covered the entire surface in fresh lava over a geologically short period, erasing the older crater record and replacing it with the volcanic plains we see today. If this happened, it would represent one of the most violent geological events in the history of the inner solar system, a planet-wide volcanic cataclysm that remade the face of Venus in a geological instant. The timing of this hypothetical resurfacing event overlaps intriguingly with the period during which the ASU carbonatite study suggests Venus's atmosphere may have undergone its final transformation. If vast quantities of carbonatite lava erupted across the surface, outgassing enormous volumes of carbon dioxide, and if this happened within the last few 100 million years, then Venus's current hellish state might not be as ancient as people assume. The planet may have been losing its habitability gradually for billions of years as the sun brightened, but the final collapse, the locking in of the extreme greenhouse state, may have happened relatively recently in geological terms. This is speculative. The evidence is not conclusive. But the 2025 ASU study and the confirmed ongoing volcanism provide new support for the idea that Venus's interior played an active role in the planet's transformation, not merely a passive one. Venus did not simply drift into its current state because it was too close to the Sun. Its own geology may have delivered the killing blow, and that changes the story profoundly. Because if Venus's fate was determined purely by its distance from the Sun, then Venus is a special case. A cautionary tale, perhaps, but one that applies only to planets in that specific orbital zone. If, however, Venus's fate was sealed by a combination of gradually increasing stellar luminosity, loss of water, loss of the carbon cycle, and massive volcanic carbon dioxide release, then the lesson is far more general. It means any Earth-like planet, anywhere in the universe, could potentially follow the same path if the right combination of factors aligned. Understanding how this happened changes what Venus means. It is no longer just a destination. It is no longer just the hottest planet, or the planet with the thickest atmosphere, or the planet where Soviet landers went to die. It is something far more unsettling. It is a demonstration, a proof of concept, an existence proof that a planet which starts out looking almost exactly like Earth can end up as one of the most hostile environments in the known universe. And it did so through processes that are not exotic, not unique to Venus, not dependent on some bizarre coincidence of alien physics. It did so through greenhouse warming, water loss, volcanic outgassing, and the failure of geological recycling. Processes that are understood, processes that obey the same laws of chemistry and physics that operate everywhere. That is what makes Venus not just interesting but frightening. Not the temperature, not the pressure, not the acid. The fact that we understand how it happened, and that understanding does not make it feel less threatening. It makes it feel more so. There is a concept in engineering called a single point of failure. It describes a component in a system whose breakdown alone is sufficient to bring down the entire system. Engineers spend enormous effort identifying and eliminating single points of failure because they represent the most dangerous kind of vulnerability, the kind where one thing going wrong cascades into total collapse. Venus does not have a single point of failure. Venus has something worse. You have now seen each link in the chain individually. The atmosphere trapping heat, the heat preventing water, the missing water breaking the carbon cycle, the broken cycle allowing carbon dioxide to build, the volcanism feeding more into a sky that can never clear. But what makes Venus a unique object of scientific horror is not any one of those links. It is that they are all load-bearing simultaneously, and they all failed together, and the failure state they produced is not broken. It is stable, it is self-sustaining. And it added one final insult that seals the trap permanently. Without a magnetic field, the solar wind continues to strip whatever trace water molecules form in the upper atmosphere, ensuring that the one substance that could theoretically restart the cycle never accumulates in meaningful quantities. This is not a planet with a problem. This is a planet that has become the problem. The distinction matters because it changes what Venus means to science. A planet with a problem is a puzzle. You study it. You identify the broken component. You learn something specific. A planet that has become a complete, self-sustaining failure state is something else. It is a warning. And what it warns about is not limited to Venus. The question that planetary scientists began asking in earnest over the last 2 decades is deceptively simple. How common is this outcome? In a galaxy where rocky planets in the habitable zones of their stars number in the billions, how many of them have followed or will follow the same path that Venus did? How many Earth-sized worlds, orbiting sun-like stars at distances that should allow liquid water and moderate temperatures, have crossed the same threshold and become permanent, irreversible furnaces? This question gave rise to a concept called the Venus Zone. The term was formalized in a 2014 paper by Stephen Kane and colleagues at San Francisco State University. The Venus Zone is the region around a star where an Earth-sized planet is likely to develop a runaway greenhouse atmosphere rather than maintain a temperate, habitable climate. It sits just inside the habitable zone, overlapping with its inner edge, and it represents the region where stellar radiation is strong enough to trigger the feedback loops that consumed Venus. The boundaries of the Venus zone depend on the type of star, its luminosity, and the properties of the planet in question. For a star like our Sun, the Venus zone begins at roughly the orbital distance of Venus and extends inward. But the boundaries are not sharp. They depend on atmospheric composition, rotation rate, cloud coverage, ocean fraction, and a host of other variables that interact in complex ways. A planet at the inner edge of the habitable zone might be safely habitable for billions of years, or it might be one volcanic episode, one slight increase in stellar luminosity, one disruption of its atmospheric chemistry away from crossing into the Venus zone and never coming back. This is where the 2025 Arizona State University carbonatite study changes the picture in a way that extends far beyond Venus itself. If Venus's transformation was driven not only by increasing solar luminosity, but also by massive volcanic outgassing of carbon dioxide from carbonatite eruptions, then the Venus zone is not purely a function of orbital distance. It is also a function of geology. A planet's internal dynamics, its volcanic history, the composition of its lavas, can push it across the threshold independently of how much radiation it receives from its star. The researchers behind the study recognized this implication explicitly. Co-author Joseph O'Rourke, an assistant professor at Arizona State University, noted that in an era when astronomers are discovering many Venus-sized planets orbiting distant stars, understanding when and why Earth and Venus took different paths is essential. The study expands the range of conditions under which a planet can tip into a Venus-like state. It means the Venus zone is not a fixed line drawn at a specific distance from a star. It is a probability gradient that extends further outward than anyone previously calculated, because internal geological processes can substitute for external stellar forcing. This has immediate consequences for how astronomers evaluate the habitability of exoplanets. The Kepler Space Telescope and its successor, the Transiting Exoplanet Survey satellite, have identified thousands of confirmed exoplanets, many of them rocky worlds in or near the habitable zones of their stars. When scientists assess whether these planets might support liquid water and potentially life, they compare the planet's orbital distance and the star's luminosity against models of habitable zone boundaries. But if the Venus zone extends further than those models assume, then some fraction of the planets, currently classified as potentially habitable, may already be Venus-like furnaces hidden behind the impenetrable curtain of their own atmospheres. We cannot currently determine which exoplanets are Earth-like and which are Venus-like from the data available. A planet the size of Earth at the inner edge of a Sun-like star's habitable zone looks identical in transit data, whether it has oceans and moderate temperatures or whether it is a 500-degree pressure cooker wrapped in sulfuric acid. The transit method, which detects planets by the tiny dimming of starlight as they pass in front of their star, measures size and orbital period. It does not measure surface conditions. It does not detect atmospheres directly. It does not distinguish between a living world and a dead one. Consider what that means in practice. Imagine a future telescope identifies a rocky planet roughly the size of Earth, orbiting a Sun-like star at a distance that places it within the habitable zone. The planet has been flagged as a high-priority target for atmospheric characterization. Resources are allocated. Observation time on an extraordinarily expensive space telescope is dedicated to capturing the faint light that filters through the planet's atmosphere during transit. Scientists detect a thick atmosphere rich in carbon dioxide. They detect cloud layers. They detect evidence of geological activity based on sulfur compounds in the atmospheric spectrum. On paper, this could look encouraging. A thick atmosphere means the planet retains heat and could support liquid water. Carbon dioxide is a greenhouse gas that, in moderate concentrations, helps maintain temperate conditions. Cloud layers could be water clouds. Sulfur compounds could indicate volcanism, which on Earth is associated with a geologically active, living world. But every single one of those signatures is also consistent with a Venus-like planet. A thick carbon dioxide atmosphere could mean a comfortable greenhouse or a runaway furnace. Cloud layers could be water vapor or sulfuric acid. Sulfur compounds could indicate healthy volcanism, feeding a functioning carbon cycle, or catastrophic volcanism, pumping poison into a sky that will never clear. Without knowing how to tell the difference, without a detailed template of what a Venus-like atmosphere looks like at every wavelength versus what an Earth-like atmosphere looks like, the most expensive and capable telescope ever built could mistake a planetary hell for a potential second Earth. Or it could dismiss a genuinely habitable world because its atmospheric signature superficially resembles the Venus template. The cost of getting this wrong is not merely academic. It determines where humanity directs its attention, its resources, and its hope in the search for life beyond Earth. That limitation is about to change, and the instruments that will change it represent the most significant coordinated effort to study Venus and Venus-like worlds in the history of planetary science. 3 major space agencies have missions currently in development that will visit Venus within the next decade. NASA is building 2 missions. Da Vinci, which stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, will send a descent probe into Venus's atmosphere. The probe will fall through the cloud layers, sampling the atmospheric composition at each altitude and taking the first high-resolution photographs of the surface from below the clouds during its descent. The mission is designed to answer specific questions about the noble gas composition of the atmosphere, which preserves information about Venus's formation and early history that no other measurement can provide. Noble gases do not react chemically. They are primordial fossils, locked into the atmosphere since the planet formed, and their ratios will tell scientists whether Venus formed with a composition similar to Earth's, whether it ever had a substantial ocean, and how its atmosphere evolved over time. NASA's second Venus mission is Veritas, which stands for Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy. This orbiter will use synthetic aperture radar to create the most detailed 3-dimensional map of Venus's surface ever produced, with resolution far exceeding what Magellan achieved in the early 1990s. Veritas will also use a near-infrared spectrometer to determine the composition of surface rocks, identifying whether different regions are made of different materials and helping to reconstruct the planet's volcanic history. The mission will search for ongoing volcanic activity, map tectonic features, and provide the data needed to determine whether Venus ever had plate tectonics and when it lost them. The European Space Agency is contributing EnVision, an orbiter designed to study Venus from surface to core. EnVision will investigate how Venus's interior, surface, and atmosphere interact, focusing on whether the planet is still geologically active and how its atmospheric chemistry is maintained. The mission will carry instruments to probe the subsurface using radar, study atmospheric dynamics, and monitor volcanic gas emissions. Together, these 3 missions represent the first coordinated exploration of Venus in more than 4 decades. The last dedicated mission to orbit Venus was the European Space Agency's Venus Express, which operated from 2006 to 2014. Before that, no dedicated Venus orbiter had operated since NASA's Magellan ended its mission in 1994. The gap between those missions and the upcoming fleet reflects a period during which Mars dominated planetary exploration funding and public attention. Venus, despite being closer to Earth and arguably more relevant to questions of planetary habitability, was neglected for decades. That neglect is ending because the scientific community recognized something that the evidence had been pointing toward for years. You cannot understand planetary habitability without understanding Venus. And this realization is inseparable from a broader one that the inner solar system has been trying to teach us for decades, if we are willing to read the lesson plainly. Our immediate neighborhood contains not 2 but 3 data points on the fate of rocky worlds: Mars, Earth, and Venus. 3 planets born from the same disk, built from the same materials, orbiting the same star. And the 3 of them produced 3 radically different outcomes. Mars was too small. With roughly 1/10 of Earth's mass, it could not hold onto a thick atmosphere. Its core cooled early, its magnetic field died, and the solar wind slowly stripped its atmosphere over billions of years. Without atmospheric pressure, liquid water could not persist on the surface. Mars froze. It dried. It became a cold, thin, desiccated husk where the atmospheric pressure is so low that exposed liquid water would boil away almost instantly, not because of heat, but because of the near vacuum above it. Mars failed by losing its atmosphere. It is the story of a planet that was too small to hold itself together. Venus failed in the opposite direction. It was not too small. It was almost exactly the right size. It kept its atmosphere. It kept it so thoroughly, in fact, that the atmosphere became the instrument of its destruction. Where Mars lost too much and froze, Venus retained too much and burned. The carbon dioxide that should have been locked in rocks accumulated in the air. The water that should have regulated the climate evaporated and was lost to space. The volcanism that should have been part of a self-regulating geological cycle instead became an unopposed source of greenhouse gas pouring into a sky that had already passed the point of no return. Earth sits between them. Not because it occupies a magical orbital position, although its distance from the Sun helps, but because it maintained, through what may be a combination of size, composition, water content, tectonic behavior, and magnetic field strength, the interlocking set of regulatory systems that neither of its neighbors could sustain. Earth is not the default outcome for a rocky planet. It is the narrow success case. Mars shows what happens when the systems never fully develop. Venus shows what happens when they develop and then collapse. Earth is the version where everything held together. So far, that 3-way comparison is the most important data set in the study of planetary habitability. It is the reason Venus science is not a niche specialty. It is foundational. Every model of what makes a planet habitable must account for all 3 outcomes simultaneously. A model that predicts Earth but cannot explain Venus is incomplete. A model that explains Venus but does not account for Mars is missing a variable. Only when the 3 stories are told together does the full picture of rocky planet evolution come into focus. There is also a private mission that may arrive at Venus before any of the government-funded spacecraft. The Rocket Lab Venus Life Finder, developed in collaboration with researchers at MIT, has been designed to send a small probe into Venus's cloud layer to search for organic molecules and other indicators of potential biological activity. The mission concept is focused on the atmospheric layer between roughly 48 and 60 kilometers altitude, where temperatures and pressures are closest to Earth-like conditions. The probe would not land. It would sample the cloud layer aerosols during a brief descent and transmit its findings before falling into the hostile lower atmosphere. This mission is motivated by a question that remains one of the most tantalizing in astrobiology. Could microbial life exist in the clouds of Venus? The hypothesis is speculative, but not baseless. The relevant atmospheric layer has temperatures between roughly 30 and 70 degrees Celsius, pressures near Earth sea level, and access to sunlight and chemical energy. Microorganisms on Earth survive in environments at least this extreme, including in acidic hot springs, in the upper atmosphere, and in volcanic vents. The 2020 phosphine detection that briefly electrified the scientific community. The claim that phosphine gas had been detected in Venus's cloud layer at concentrations that could not be explained by known non-biological chemistry brought this question into the global spotlight. The original detection was subsequently challenged. Reanalysis showed the data had processing errors, and the detected levels were far lower than initially reported. A 2023 observation using the Stratospheric Observatory for Infrared Astronomy failed to detect any phosphine in the relevant atmospheric region. The scientific consensus as of today is that the phosphine detection is not confirmed and should be interpreted with significant caution, but the interest it generated was not wasted. The phosphine debate forced planetary scientists to confront how little we actually know about Venus's atmospheric chemistry. The cloud layer remains one of the least characterized environments in the inner solar system, and a 2025 study published in JGR Planets added a surprising new dimension to the picture. Researchers reanalyzed data from NASA's Pioneer Venus mission, which sent a probe into Venus's atmosphere in 1978. The reanalysis examined aerosol data collected by the large probe's instruments during its descent and reached a startling conclusion. The cloud aerosols on Venus contain approximately 60% water by mass, roughly 3 times more than previously estimated. The dominant composition is not concentrated sulfuric acid, as had been the scientific consensus for decades, but water hydrates and iron sulfate, with sulfuric acid present, but not as the majority component, if confirmed by future missions. This finding would substantially alter our understanding of Venus's cloud chemistry and the potential for those clouds to support microbial metabolism. It would also mean that after all the water Venus lost from its surface and upper atmosphere over billions of years, a surprising reservoir of water may persist locked in the aerosol particles of the cloud layer, hidden in plain sight for nearly 50 years in data that scientists had not fully re-examined. This is the state of Venus science today. Fundamental discoveries are still being made from decades-old data. Basic questions about the planet's atmospheric composition, geological activity, and potential for even microbial habitability remain open. Venus is the closest planet to Earth, one of the most observed objects in the night sky, and we still do not know with certainty what its clouds are made of. The upcoming missions will begin to close these gaps. But the gaps themselves are a reminder of how profoundly Venus has been neglected relative to its scientific importance, and its scientific importance extends far beyond Venus itself. Every rocky exoplanet that astronomers identify in the habitable zone of its star carries the same fundamental question that Venus poses. Did it stay habitable, or did it cross the line? When the James Webb Space Telescope or the Future Habitable Worlds Observatory examines the atmosphere of a rocky world orbiting a distant star, looking for biosignatures, the chemical evidence of life, the most important comparison point will not be Earth alone. It will be Venus, because the absence of biosignatures does not necessarily mean the planet is a dead rock like Mars. It might mean the planet is a living furnace like Venus, geologically active, atmospherically dynamic, and completely uninhabitable despite having every physical qualification to be a second Earth. The ability to distinguish between these two outcomes, between a Mars-like failure and a Venus-like failure, will be one of the most important capabilities in the next generation of exoplanet science. And building that capability requires understanding Venus first. We need to know exactly what Venus's atmosphere looks like at every altitude, what chemical signatures it produces, and how those signatures differ from what a habitable planet would show. Without that baseline, we risk misinterpreting exoplanet data in ways that could either falsely identify dead worlds as alive or, perhaps worse, falsely dismiss Venus-like worlds as simply barren when they are in fact actively hostile. This brings us to the final dimension of the Venus story, and it is the one that sits heaviest, not the science, not the missions, not the engineering challenges or the atmospheric chemistry or the exoplanet implications. The weight of Venus comes from something simpler and more personal. It comes from the recognition of what Venus represents when you stand back far enough to see the full shape of the story. Venus is not a monster. It is not an aberration. It is not a cosmic accident or a freak outcome that required some exotic, unrepeatable set of circumstances. Venus is what happens when an Earth-like planet loses a set of interconnected systems that, on Earth, we take entirely for granted. Liquid water on the surface, a functioning carbon cycle, active plate tectonics that recycle atmospheric carbon dioxide into rock, a magnetic field that protects the atmosphere from stellar wind erosion. These systems are not luxuries. They are not redundancies. They are the machinery that keeps Earth habitable, and on Venus, every single one of them broke. The water evaporated and was lost to space. The carbon cycle collapsed without water to drive it. Plate tectonics ceased without water to lubricate the mantle. The magnetic field never functioned in the way Earth's does, possibly because the absence of plate tectonics altered the thermal evolution of the core. And without these systems, the planet had no mechanism to prevent carbon dioxide from accumulating in the atmosphere, no way to regulate its own temperature, no defense against the slow brightening of its star. The systems that failed were not independent. They were coupled. Each one depended on the others. And when one fell, it pulled the rest down with it. What Venus teaches is that habitability is not a feature of a planet's specifications. It is a feature of a planet's active processes. Earth is not habitable because it is the right size, at the right distance from the right star. Earth is habitable because it maintains a set of interlocking, self-regulating systems that actively prevent the planet from drifting into an uninhabitable state. Those systems are running right now. The water cycle is turning, the carbon is being buried, the plates are moving, the magnetic field is deflecting. And because they run silently, in the background, on timescales that dwarf human attention, it is easy to assume they are permanent, guaranteed. Part of the planet's identity rather than its ongoing activity. Venus is the evidence that they are not permanent. Venus had most of the same raw specifications as Earth. It may have had liquid water for 2 billion years, and it still fell. It still crossed the threshold. It still locked itself into a state that no intervention, no geological process, no amount of time on any humanly meaningful scale can reverse. The transformation was not caused by a cosmic impact or a freak stellar event. It was caused by the same types of processes that operate on Earth, just slightly out of balance, just enough to tip the feedbacks in the wrong direction. This is not a metaphor. It is not an analogy being stretched for dramatic effect. It is the literal conclusion of the planetary science. Venus and Earth started with the same ingredients. One maintained its regulatory systems, the other lost them. And the difference in outcomes is the difference between the planet you are sitting on right now and a world that would crush, melt, dissolve, and suffocate you simultaneously under a sky you would never see, in an atmosphere too thick and too toxic to breathe, on a surface too hot for any known biology, any known electronics, or any known structural material to survive for more than minutes. Scientists do not call Venus the scariest planet because it has the highest temperature or the greatest pressure or the most corrosive clouds. Those are symptoms. They call it the scariest planet because of what it proves is possible. It proves that a planet, almost identical to Earth, formed from the same materials at the same time, in the same neighborhood, can become one of the most hostile environments in the entire solar system through a self-reinforcing chain of failures that, once started, cannot be stopped. It proves that there is nothing inherently protective about being an Earth-sized rocky world with a thick atmosphere and an iron core. Those specifications do not guarantee a habitable outcome. They are necessary conditions, but they are not sufficient. And it proves one more thing that is perhaps the most difficult to sit with. There is no evidence that Venus did anything unusual to arrive at its current state. It was slightly closer to the Sun. The Sun gradually brightened. Water vapor accumulated in the atmosphere. The oceans evaporated. The hydrogen was lost to space. The carbon cycle broke. Volcanic outgassing continued unopposed. The feedbacks reinforced each other. The system locked. Every step in that chain is governed by physics that is well understood, chemistry that is straightforward, and geology that is ordinary. Nothing in the Venus story requires invoking unknown processes or exotic mechanisms. It happened through normal planetary science, operating on normal timescales. That is the source of the discomfort. If the transformation of Venus required some bizarre, unrepeatable event, you could file it away as a curiosity, a strange outcome for a strange planet. You could put it in a category separate from Earth and move on, but it did not require anything strange. It required only that the conditions be slightly different, the feedbacks slightly stronger, the margins slightly thinner, and that means the Venus outcome is not a category error. It is a category that Earth-like planets can fall into, not easily, not inevitably, but possibly. Under the right combination of circumstances, any world walking the narrow path of habitability can step off that path and into the trap that Venus fell into. And the trap does not let go. The next generation of Venus missions will descend through those sulfuric acid clouds, sample the atmosphere molecule by molecule, map the volcanic surface in resolution we have never achieved, and search for the chemical fingerprints of what Venus was before it became what it is. They will look for noble gas signatures that reveal whether Venus had an ocean and for how long. They will look for rock compositions that tell us when the last volcanic catastrophe resurfaced the planet. They will look for atmospheric chemistry that might, against all expectation, harbor traces of microbial metabolism persisting in the one narrow band of altitude where conditions allow it. What they will not find is a way to undo what happened. Venus is past the point of recovery. The transformation is complete. The system is locked. What was once potentially a second Earth is now a permanent monument to what an Earth can become when its self-regulating systems fail and its feedbacks turn against it. When you look at Venus in the night sky, that brilliant white point of light hanging near the horizon just after sunset or just before dawn, you are not looking at a distant, alien curiosity. You are looking at the nearest planet to Earth, your closest neighbor in space, a world almost exactly your size and your composition and your age. You are looking at a planet that may have had oceans when the first complex life was appearing on Earth. You are looking at a world that lost everything, not through violence, not through catastrophe, but through a slow, grinding, self-amplifying failure that converted a potentially habitable world into a permanent planetary furnace. That is why Venus is the scariest planet in the solar system. Not because of what it is, because of what it was, and because of what it proves an Earth-like world can become.